We've mapped Mars, sent probes into deep space, and studied the moon in detail. Yet on Earth, the ocean, covering over 70% of the planet, remains largely unexplored, especially below 200 meters. Most of what we know comes from a thin surface layer. Everything below it is still partially unknown. We split it into zones, like levels in a video game. In the sunlight zone, 0 to 200 meters, we think we know a lot. Whales, sharks, coral reefs, everything looks familiar. But even here, tiny invisible ecosystems are still being discovered and studied. Go deeper into the twilight zone, 200 to 1,000 meters, and things get weird. Billions of creatures move up and down every single day in a giant migration we can barely track. Then comes the midnight and abyssal zones, 1,000 to 6,000 meters. A place so dark and massive that most of it has never been directly seen by humans. Every time we send a machine down, it feels like the ocean is saying, "Oh, you're still here? Let me show you something new." And finally, the Hadal Zone, 6,000 meters plus. Places like the Mariana Trench, where pressure is so extreme it can crush most submarines instantly. We know the depth of the deepest point on Earth, but what actually lives there? That's where things stop being known and start becoming mystery. So today, we're diving into the 8 biggest ocean mysteries scientists still can't explain. And some of them are so strange, they sound fake, but they're not. The Bermuda Triangle is a loosely defined area in the western North Atlantic, typically between Florida, Bermuda, and Puerto Rico. It became famous due to reports of unexplained disappearances of ships and aircraft, especially during the 20th century. Despite its reputation, it is one of the most heavily traveled maritime and flight regions in the world, meaning accidents are statistically expected at high volume. Flight 19, 1945. A group of 5 U.S. Navy bombers disappeared during a training mission. The pilots reportedly became disoriented, ran out of fuel, and vanished. A rescue plane sent to search for them also disappeared. Most evidence suggests navigation error combined with poor weather and compass issues. USS Cyclops, 1918. A U.S. Navy cargo ship with over 300 people on board vanished between Barbados and Baltimore. No distress signal was sent. Common explanations include structural failure, overload, and severe weather. No wreckage was ever confirmed. Common theories. Magnetic anomalies. Claims of compass malfunction in the region. Scientific surveys show no unusual magnetic behavior beyond normal variation. Methane hydrate eruptions. Gas release from seabed could reduce water density, potentially sinking ships suddenly. This is possible, but not confirmed in historical cases. Human error plus weather. The region is known for fast-forming storms, strong Gulf Stream currents, and heavy traffic routes. The Bloop. In 1997, the U.S. National Oceanic and Atmospheric Administration, NOAA, detected a massive low-frequency underwater sound in the South Pacific. It was recorded by hydrophone arrays placed thousands of kilometers apart. What made it unusual was not just the detection, but the intensity. The signal, later nicknamed the Bloop, was powerful enough to be heard across a range far larger than typical biological sources. At first, it did not match any known marine animal in size, energy output, or acoustic pattern. Key characteristics. Extremely low frequency, meaning it could travel vast distances underwater. Detected multiple times by independent sensors. Origin point estimated in a remote area of the South Pacific. Signal pattern inconsistent with known whale vocalizations or geological noise at the time. Early public curiosity led to theories involving unknown giant marine species, deep-sea volcanic activity, unknown geological events. Later analysis by NOAA linked the signal most likely to ice-related fracturing events, such as large Antarctic icebergs cracking or separating from ice shelves. These events can produce extremely powerful acoustic signatures that travel long distances underwater.
Deep-sea gigantism. Deep-sea gigantism is a biological pattern where certain species grow significantly larger in deep ocean environments compared to their shallow water relatives. It is observed in multiple groups, including crustaceans, cephalopods, and amphipods. Examples include the giant isopod, a crustacean related to pillbugs reaching over 30 centimeters. deep-sea amphipods that grow several times larger than surface species, the giant squid, which can reach lengths over 10 to 12 meters, the even larger colossal squid, one of the most massive invertebrates on Earth. Where it occurs. This phenomenon is mostly found in bathyal zone, 1,000 to 4,000 meters, abyssal plains, 4,000 to 6,000 meters, occasionally in hadal trenches. These environments share near freezing temperatures, extremely high pressure, low food availability, permanent darkness. Main hypotheses. Scientists have not confirmed a single cause, but several mechanisms are proposed. 1. Temperature effect, metabolic rate. Cold water slows metabolism, allowing longer lifespans and extended growth periods. 2. Oxygen availability. Some deep waters contain higher dissolved oxygen, which may support larger body sizes. 3. Reduced predation patterns. Fewer predators may allow organisms to grow larger without early mortality. 4. Energy storage advantage. Larger bodies may store energy more efficiently in food-scarce environments. What is still unknown? Even though patterns are clear, the exact biological driver is unresolved because deep-sea species are extremely difficult to observe in life. Many specimens are only collected dead or damaged. Laboratory pressure conditions are hard to replicate accurately. Growth cycles of deep species are still largely untracked. Why it matters. Deep-sea gigantism challenges simple biological rules like resource limitation equals smaller size. It remains one of the clearest examples of how extreme environments can reshape life in ways we still do not fully understand.
Bioluminescence is a fast-paced tone. Bioluminescence is the ability of living organisms to produce light through chemical reactions inside their bodies, usually involving luciferin and luciferase-type enzymes. In the deep ocean, it is not rare. It is dominant. It is estimated that a large fraction of midwater and deep-sea organisms can produce light in some form. This includes fish, jellyfish, squid, crustaceans, and even bacteria. Where it dominates. Bioluminescence is most common in mesopelagic zone, 200 to 1,000 meters, bathopelagic zone, 1,000 to 4,000 meters, some abyssal and hadal environments. Below about 1,000 meters, natural sunlight is absent, making bioluminescence one of the primary signals in the ecosystem. Main functions, still debated. Scientists agree it serves multiple roles, but no single explanation covers everything. 1. Communication. Some species use light patterns to signal mates or coordinate behavior in complete darkness. 2. Predation, luring prey. Certain organisms use light as bait, attracting prey closer before striking. 3. Defense, startle or confuse. Some species release glowing clouds or flashes to disorient predators. 4. Camouflage, counter-illumination. Some fish produce light on their underside to match faint surface light from above, making them harder to detect. Why it is so widespread. The deep ocean is completely dark, vast and low density in life, difficult for sound and chemical signals to travel precisely over long distances. In this environment, light becomes a universal signaling tool, so evolution repeatedly selected it across unrelated species.
The Baltic Sea Anomaly is a circular-shaped structure discovered in 2011 by a Swedish treasure hunting team using sonar imaging. It lies at roughly 80 to 100 meters depth in the Baltic Sea, between Sweden and Finland. What made it viral is its appearance. In sonar scans, it looked unusually structured, almost like a disk with straight edges and angular features, unlike typical natural seabed formations. Discovery. Detected using side-scan sonar during a shipwreck search mission. Reported diameter, 60 meters. Located on a relatively flat seabed. Follow-up dives were limited due to poor visibility and technical constraints. Early images showed shapes that some interpreted as stair-like structures, a central depression, and sharp angular lines inconsistent with common sediment formations. Scientific explanation. Most geologists and marine scientists explain the structure as a natural glacial formation. The Baltic region was heavily shaped by Ice Age glaciers. Moving ice sheets can carve, deposit, and compress sediments into unusual geometric-looking structures. Rounded rocks, moraines, and erosion patterns can appear artificial in sonar imaging due to resolution limits. Why it caused controversy. The anomaly gained attention because sonar images can exaggerate symmetry and edges. Early public interpretations were based on low-resolution scans. Some features resembled man-made geometry, fueling speculation about artificial origin. However, no physical evidence of tools, construction materials, or engineered structures has been confirmed. Current consensus. The majority scientific view is it is a natural geological formation shaped by glacial processes. But key limitations remain. Only limited direct sampling has been done, visibility and conditions in the area make detailed inspection difficult, and sonar interpretation can be misleading without ground truth data. Rogue waves are extremely large, isolated waves that appear suddenly and can reach heights of over 20 to 30 meters, sometimes even higher. They were once dismissed as sailor myths because standard wave models predicted that such extremes were nearly impossible. That changed in 1995 when a massive wave struck the Draupner platform in the North Sea. Sensors recorded a single wave of about 25.6 meters, while surrounding waves were much smaller. This became one of the first scientifically confirmed rogue waves. What makes them different? Rogue waves are not regular storm waves. They are isolated, a single massive wave among normal seas, extremely steep and powerful, unpredictable in timing and location, capable of appearing in relatively calm conditions. How they form? Theories. Scientists have several explanations, but no single confirmed mechanism. First, wave interference, constructive overlap. Smaller waves can align in phase, briefly combining into one giant wave. Second, focusing by currents. Strong ocean currents can compress wave energy into a narrow region, increasing wave height. Third, nonlinear wave dynamics. Ocean waves don't always behave linearly. Energy can shift and amplify unexpectedly. Why they are dangerous? Rogue waves are a major hazard because ships are designed for expected maximum wave heights. They can appear without warning. Their vertical walls can exceed ship stability limits. They can cause sudden structural failure or capsizing. What we still don't know. Even though rogue waves are now confirmed, key questions remain. How often they occur in different ocean regions? Which conditions most reliably trigger them? Whether some ocean zones are more prone than others? How to predict them in real time? Current forecasting models still struggle because rogue waves are rare, short-lived, and influenced by multiple overlapping factors. Rogue waves proved that the ocean can still break its own rules. What was once considered impossible is now confirmed, but still not predictable, making them one of the most dangerous and least controllable ocean phenomena known to date.
The Mariana Trench is the deepest known part of the world's oceans, located in the western Pacific Ocean near Guam and the Philippines. Its deepest point is the Challenger Deep, reaching roughly 10.9 kilometers below sea level, deeper than the height of Mount Everest. At this depth, conditions are extreme. Pressure exceeds 1,000 times surface pressure. Temperature is just above freezing. No sunlight reaches the bottom, and food supply is extremely limited. Despite its size and importance, exploration is extremely limited. Only a handful of crewed dives have ever reached the bottom. Robotic missions have sampled only small areas. Most of the trench remains completely unobserved. In reality, we have physically studied only tiny points compared to its full length of over 2,500 kilometers. Even in these extreme conditions, life has been found. Microorganisms adapted to high pressure, deep-sea amphipods and small invertebrates, specialized ecosystems that rely on falling organic matter, marine snow. These organisms survive without sunlight, using chemical and detritus-based energy sources.
Milky Seas phenomenon. Milky Seas are rare ocean events where large areas of the ocean surface glow continuously, sometimes covering thousands of square kilometers with a soft, uniform light. Unlike typical bioluminescent flashes caused by disturbed plankton, Milky Seas appear steady, widespread, and long-lasting. Historical reports from sailors describe entire horizons glowing at night, a smooth, white-blue illumination rather than flickering light, duration lasting hours to days, no obvious surface disturbance, no waves or storms needed. Modern confirmation is limited, but satellite data has occasionally detected similar large-scale luminous events in remote ocean regions. Main explanation. The leading hypothesis links Milky Seas to massive blooms of bioluminescent bacteria, especially species similar to bioluminescent systems found in marine microbes. In this scenario, bacteria attach to organic particles or plankton. They produce continuous light rather than flashes. When present in extremely high concentrations, the light becomes visible over vast areas. Why it is still not fully understood. Despite the bacterial explanation, several problems remain. Direct sampling of active Milky Sea events is extremely rare. Most observations are anecdotal or historical ship reports. Conditions required for such large-scale bacterial synchronization are unclear. Satellite detection confirms light, but not always the exact biological source.